Hey folks! Okay, last time we took a look at top-down parsing, so this time we want to take a look at bottom-up parsing, and we'll spend a couple of sessions on this. So again, the idea is if we're thinking of this in terms of the parse tree for a particular chunk of source code or token sequence, then we're working our way up the tree. We're starting from the tokens at the bottom of the tree, and we're gradually applying a derivation rule at a time to work us one step at a time up the tree until eventually we arrive at the root, is the idea. So the sequence of tokens and non-terminals that we're working with at kind of the bottom edge of our tree right now, we'll call the frontier. And the rule that we pick to move one step up is going to be called the handle. So that'll be replacing, one sequence of the tokens or non-terminals with a new left-hand side non-terminal, if you like, from a rule. So this is the process that we're going to take a look at. And we'll see how we go here. All right, so let's say we've got a really simple grammar for just a simple statements. So a statement is going to be made up of a data type, an identifier for a variable, an assignment state, an assignment operator, and then some kind of an expression. And so the type and the expression are non-terminals, and the var is a token type, and the EQ is a token type. So our expressions can either be just a value or a negative sign and a value. And a value can be either a number or an identifier, a variable. And then our data type can be either an int data type or a real data type. So this is for things like, int foo equals negative 27, kind of a variable declaration. So this is the idea. And let's use that int foo equals negative 27 as our example to work our way up the parse tree. So in terms of just the token types there, we'd have an int token type, a var token type, an EQ, a minus, and a num as our token types. So in reality, we'd probably have, for some of these, we'd have some kind of properties associated with them. So for instance, with the var token type, we would also remember what actual identifier it was, foo. And maybe if there were different kinds of assignment operator, we might remember specifically which one. So it might be the equal sign, for instance. Or if there were different kinds of negation operators somehow, then we might remember which specific one we were dealing with, right? For the numeric value, we'd probably want to remember what actual number it was, so 27, for instance. So if we're thinking about our tree at the bottom level there, we've got this sequence of tokens, and they might each have some properties associated with them. So now we want to try and work our way up from that, our starting frontier, up towards the statement, the top level non-terminal, if you like. So we'll just go through this list of tokens sort of one at a time from left to right and see if we can see things that we can use to replace with one of our grammar rules. So starting from that left-hand side, I see this int token. Well, I've got a rule that says type goes to int. So I could replace that int with type, my non-terminal, and say, okay, well, I'm going to assume that that's how I got at int, was I had this derivation applied. So I build that one step of the tree. And so now my frontier is type, and then var EQ minus num. Right? So it's just we're just keeping track of the pieces that we're trying to work on as we go. And if we keep going through this, then there's nothing sort of type var. There's nothing on the right-hand side here that's just purely type var or type var EQ or type var EQ minus. So we're gradually going through this list, this frontier, trying to see if there's a rule that I can apply for the pieces that I've got so far. Once I get all the way down here and I see this num, I can go, oh, wait a minute, there is a rule that goes to num. So I can say, val goes to num. So I'll replace num with val. And so now my frontier is type var EQ minus val. Right? So I'm gradually working my way up. Now again, there's nothing in these rules that say type var EQ minus val. So we're looking for pieces in this that will match the right-hand side for one of our rules. And we see this chunk, the minus val, that can come from an expression. So I'll replace those two with expression. So now my frontier is type var EQ expression. Wait, I've got that as the right-hand side of one of my rules. That can come from statement. So I replace those four with statement. And now I've actually got my parse tree, right? I've used up I've used up my entire frontier, if you like, and I've made it to the root. And so this would be an example of building up our parse tree from the bottom up. All right. So again, we've got this idea of the handles being essentially the derivation rule that we're trying to apply to get one more step up the tree. So the big problem that we have is picking the correct handle. Right? This is the same idea as when we were doing our top-down parsing. The big trick was figuring out what rule to apply next in our derivation and which non-terminal to apply it to. Right? We're running into the same situation, just going from the bottom up instead of from the top down. So I'm going to refer to the handle that we're interested in as, some non-terminal goes to some sequence of terminals and symbols, and a position that we're in the sequence. So where X ends in our sequence, our current sequence of tokens and non-terminals in the frontier. So here's our frontier, right? A bunch of tokens and non-terminals. And then wherever this right-hand side of A ends, so A goes to blah, 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 wherever the blah, blah, blah ends in here is the position that we're interested in, this K position. So I'm just going to kind of use this notation to refer to, A goes to some chunk X, and X ends at position wherever in our current frontier. I'm going to call the step of replacing this X sequence with the non-terminal A as a reduction, because X is likely to be it's at least one symbol, but it's likely multiple symbols of tokens and non-terminals. And as we go up the tree, we're replacing that chunk. Maybe I'm replacing X1, X2, X3 with A. So I'm replacing a bunch of things, or at least one thing, with a non-terminal. So I'm reducing the size of my frontier. So we'll call this a reduction. And what would happen as we're doing this, when I choose this rule to apply, then what I'm going to do in terms of my parse tree is say, I've got to generate one new node in my parse tree up above where I am now, and it's going to be the parent of whichever tokens and non-terminals I replaced on that right-hand side. So we're working our way up. And again, logically we're just saying, here's the two pieces. I'm replacing, let's say, minus and val with expression. So I build a node for expression and link it to the nodes that I had for minus and for val. All right, so we're working our way up. And again, if you're thinking about the relationship between top down and bottom up, if you think about the derivation that you would apply to get to a particular string, so let's say I had some start symbol, and I went from there to x, y, and z, and I went from there to foo, y, z, and from there to foo, and z, and from there to foo, and blah, and I wound up with my final tokens for the sequence. Really what we want in our bottom-up approach is to do that in the reverse order, right? We want to look at foo and blah and recognize that I can replace blah with z, and then look at foo and z and recognize that I can replace and with y, and look at foo, y, z and realize that I can replace foo with x, and then look at x, y, z and realize I can replace that with start. So you're really just ideally doing your derivation in reverse. So if you've got this derivation that's this nice linear sequence of steps, in an ideal world, our bottom-up parse goes through that same linear number of steps, right, a proportional number of steps to work its way back towards the root. All right, so again, we've got different classes of grammars and parsers that work well for this and others that don't. So LR1 parsers are those that scan symbols from left to right. So if you've got your starting list of tokens, you're going through them from left to right. So the L stands for you're going through your tokens left to right, or through your frontier left to right. The R refers to a rightmost definition in the grammar. So the grammar rules that we're using for bottom-up aren't doing leftmost derivations, they're doing rightmost derivations. So they're doing derivations on the rightmost non-terminal. And again, the 1 refers to the idea that we're allowed to look ahead at the next symbol in input. So we're going to go through and take a rightmost derivation and build it in reverse, is the idea. So we'll play with an example here. Let's say this is the grammar that we're going to consider. So I've got a program that starts with the keyword begin, ends with a begin token, and has an end token at the end. It's got a list of statements in the middle. Our list can be either a list of statements followed by a statement or just a single statement. So if you recall, in the leftmost derivation, we said it could either be a statement followed by a list or a statement. Since we're doing a rightmost derivation this time, we just kind of reverse the order of those two things, just so we don't want to wind up with infinite right recursion issues. So a list can be either a list followed by a statement or a single statement, so this way you can get a whole slew of statements in a row. A statement can be one of three things. Either a variable equals some assignment value and then a terminator, so a semicolon for instance, so x equals 37 semicolon type of idea. A print, your identifier and the terminator, or essentially a declaration where you've got a data type, an identifier, and a terminator. So we've got these three kinds of things that we can work with. And then for the assignments in here, we'll either say it can be an identifier, an equal sign, and another one of these things, or it can end in an integer literal or a real literal. So these together with the statement, this can essentially give you something like x equals y equals z equals 37 and a semicolon, for instance. So this is the style of grammar that we want to work with, and we'll just play with this in an example. All right, so if we think about this as our sample program where we've got begin, int x, int y, x equals y, 10, and a print x and an end, right? This matches the grammar rules that we laid out before. Our token sequence, right, if we're just looking at what the token types for these things are and ignoring the properties we'd associate with them, we've got a begin, an int var and a terminator, an int var and a terminator, a var equals a numeric value and a terminator, and then a print var and a terminator and an end. Right? So this is the token sequence, and we'll just work from this token sequence and see if we can work our way up the tree. So if we're going through this, again, we've got this sequence that we're trying to read our way through, and so we see the begin, and there's no rule whose right-hand side is just begin. As we keep going through this, if we start looking at our the right-hand sides of our rules, we'll see one that's got the int var term. So we can look at this one and go, wait a minute, that's a valid chunk for a statement. Right? If we look back at our grammar rule, int var term was a valid statement. So we go through and replace that with a statement. And so now our new frontier is begin statement blah, 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 blah. So statement could be a list. If you recall from, again, our grammar rules, we've got list can be a single statement. So now we can replace statement with list. So now we've got begin list and then the rest of it. So as we work our way through this, right, so we've got the begin, the int var term, we've replaced that with statement and then with list. So now we've got begin, list, and then we're picking up here so now we've got begin, list, and then int var term, blah, 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 blah. So again, we just keep plowing our way through this. And now we see that next int var term and go, wait a minute, that's a statement. So now we replace those three with statement. And so now our frontier is begin, list, and statement, right? Where this statement is the one that we just did, and the list is the one from earlier. Well, again, we've got a grammar rule that says list statement is the right-hand side of list. So we can replace those two with list. Right? So now we've got begin list, and then we're on to, going the wrong way. So now we've got begin and list, and that covers this stuff, and we're on to the var equals. Right? So we keep reading through our tokens, and so we've got begin, list, var equal, inum. So far as we're going through this, this isn't the right-hand side of any rules. Oh, but wait, we see inum, and that is the right-hand side of a rule. And assign can go to inum. So we replace that inum with assign. So now we've got begin, list, var equal, assign. Ah, that var equal assign is the right-hand side of a rule. It's an assign. So we can replace that with assign, and we just keep plowing our way through this, right? So now we've got begin, list, var equal, assign, and then there's a terminator. And we can recognize that and go, oh, wait a minute, that's a statement. So now we get begin list statement, and then whatever's left after that. Well, again, list statement can come from list. So we replace that with list. So now we've got begin list, and then on with the rest of it. So we've got this is all covered by begin list. And so we pick up with that print. And again, you get the idea. We're going to see that print var term and go, hey, wait a minute, that's a statement. So now we've got begin list statement, and we can replace that list statement with a list. So we've got begin list, and all that's left is the end. So now we've got begin list end, and we go, ah, wait a minute, that's prog. So finally, we've reached the root, we've used up all of the tokens, and we've actually built our parse tree. Now, in reality, you would probably get this to actually display or to record somewhere, either to build the parse tree as it goes, so build nodes for it, or to display what derivation rules it was applying. So it's saying something like, okay, here's the derivation rule that I'm applying to, and here's the list of symbols, tokens, and non-terminals that I'm applying it to, so that we can actually follow through the chain when we want to use this in practice. But that's the idea for our derivations. So this is all well and good, but we want an algorithm to actually go through and do this for us. So remember we had a stack-based algorithm for top-down. We're going to use a stack-based algorithm for bottom-up. So we're going to have a stack keeping track of the things that we're working on, and we'll start that off as empty, and we're going to start working our way through our frontier. So that's going to be just at the beginning of the input to start off with. And then we're going to keep going until the stack is empty and we've used up all our input. So what we'll do is as we read things, as we read symbols from our frontier, we'll stuff them onto the stack. And if we look at the things that are on top of the stack right now, if they match the right-hand side of a rule, then we'll pop them off and replace them with the non-terminal from the left-hand side of the rule. So for instance, if we've got an X and a Y on top of the stack, Y on top and X underneath it, then we can say, okay, I'm going to pop the X and the Y off and replace it with an A. So we're going through this process, and if the stuff on the top of the stack is something we can replace, we'll replace it. Otherwise, we'll keep reading through the input, right? We'll keep reading through the input, whatever my frontier is, right? Throwing things on top of the stack. And in theory, eventually, as we're doing this, as we're reading through our tokens and pushing them on the stack, and then popping stuff off and replacing it with other non-terminals eventually, if the derivation is valid, we should arrive at the point we did in our example, where we've got empty input, and really the only thing left on the stack is our root non-terminal. And at that point, we can say, okay, well, that root is the one we're looking for. We've reached our goal. So this is the algorithm, but of course, again, the big trick is looking at those things on top of the stack and figuring out if they're the right-hand side of a rule. So the way we've got it expressed right now is every time we go through this while loop, we'd be looking our way down through the top of the stack, seeing if the things that are on top there match the right-hand side of any of our different rules. So we'll tweak this just a little bit and say, instead of actually having the stack record the sequence of things that are there, we'll also have it keep track of what kind of a state we're in, something that represents the collection of tokens and non-terminals we have on the top of the stack right now. So this can kind of record information like, I'm 3/4 of the way through a variable declaration, for instance. And there'll have to be some way in this to keep track of the different possible states we can be, but this is going to be our notion. We'll have some set of states that represent our different parsing conditions, and the state combined with whatever's next in the input will be what allows us to pick what rule we're going to apply next and use it to pop things off the top of the stack and replace with a new non-terminal. So the trick here is going to be figuring out what those states are, essentially building a finite state machine that accurately represents the possible states we could be in and allows us to pick our handles based on that. So for instance, if we're looking at a particular grammar rule, if we've got A goes to XYZ, then if we're thinking XYZ is what we're trying to parse right now, one state we could be in is before the X, or another is just after the X, or just after the Y, or just after we've seen the Z. So we've got these different states associated with this one particular rule. Now, in fact, there might be a couple of different sets of states based on how we got to A as well. So there might be a kind of a version of this rule for if we got to A through one path, and another version of another state for this rule if we got to A through a different path, but we'll get to that. So when we're going through looking at these stack-based algorithms, we'll be thinking about the handle that we're trying to apply, we'll be thinking about the state that represents how we got there and where we are in the current process of going through the right-hand side of A. So we'll be recording positions and states and the sequences of tokens and non-terminals. And our decision to shift, which is the idea of just grabbing the next token and pushing it on the stack, or reduce, which is applying one of these rules, popping a bunch of stuff off the stack and replacing it with a non-terminal, is going to be based on what state we're in now and what's next in the input. So we'll look at this in a practical sense in our next session, but that's the gist of where we want to go. So we'll have a few different approaches that we can take with this, just like we did with scanners. Remember, with scanners, we could either go with just a hand-coded approach, or we could have something that was auto-generated where we had a stock algorithm and we generated different tables that would tell us how to make our transitions. So in this case, our tables would be telling us, okay, well, if I'm in this state now and I see this token, should I be doing a shift or reduce? If I'm doing a reduce, which one should it be? What should I push on the stack? That kind of information. So we can either take a table-driven approach, or we can take a direct coded approach where it looks at the same sort of information as the table, but actually hard codes code to jump around between those different states and to either push stuff on the stack or to pop stuff off the stack and replace it with something new. So we've got similar issues in terms of efficiency as well. Are you better off with a table? How big's the table going to be? How slow is it going to be to look things up in the table versus the direct code approach? How fast is it going to be? How much space is your executable going to take up? Again, the loss of flexibility because you've got this hard-coded version that only works for the one language. Right? So similar issues as we looked at with our scanners. Now, again, when we're going through and actually running our algorithm, we want to make sure that we actually know what we did, right? It's not simply about is the token sequence valid. It's also about, well, what does it mean? So we're either going through and building this parse tree or recording our derivation sequence so we know which reduction rule we applied and which sequence of tokens and non-terminals we applied it to. So these are all things that we're going to try and keep track of when we try and build this out. Now, there are limitations. Not all grammars are LRK, so again, working from left to right, rightmost derivation, case symbols of look ahead. You're not guaranteed to be able to come up with an LRK grammar for the language that you want. So sometimes you can't tell whether you're supposed to use a shift or a reduce. And if you know you're supposed to do a reduce, sometimes you still can't pick which grammar rule it is you want to use. So in practice, for languages that aren't LRK, you'll often find developers introducing heuristics that say, okay, if you can't pick whether to shift or reduce, then by default reduce. Or if you can't pick which rule to apply next, here's a priority sequence for the rules. Pick this one before this one, and pick that one before this one, etc., etc. Just as a bit of an aside for now, the LRK, where you can have multiple symbols of look ahead, and LR1 are equivalent in terms of the languages that can be recognized, but LRK often allows you to produce simpler grammars to do the same thing. So we're going to focus on LR1, but you will often see cases where folks look at LRK as a way of simplifying the grammar that they're going to work with. All right, so that's kind of our overview of our bottom-up parsing. In our next session, what we'll do is look at one of these table-driven approaches where we say, let's have a set of tables that tell us what rule to apply, whether we should be doing a shift or reverse or reduce, and how we can go through and construct those tables, because the construction is going to be the big challenge. All right, that is where we will leave this one for now.